Hello, everyone. This is Professor DePaulo. Welcome you back to Site 220 Behavioral Statistics fully online. And in this week's topic, we're going to be talking about the distribution of sample means and using z-scores with samples, along with the central limit theorem and other related ideas that'll prepare you for hypothesis testing, which is going to be coming up in the next several chapters. So I'll be talking about the distribution of sampling means used to test a hypothesis and how we develop this distribution of sampling means. Then I'll be talking about the correlates of the central limit theory, which is basically dictating the shape and the expected values and the standard deviation of those sampling distribution of means that we're going to be creating. And then I'm going to extend the z-score formula that we learned last chapter, which was the z-score for individual scores in the population. And we'll shift it to the context of using z-scores to compare a sample mean to a population to see if the sample mean is different from the population mean. And then we're going to turn that into probabilities using that same table that we used last chapter, the unit z table, and we're going to be doing basically the same z-scores, but instead of using x, we're going to be using mean of the sample in replacing that x, and we're going to replace the standard deviation with the standard error. So this seems a little bit more complicated. It's not really more complicated. It's just going from one single score to a mean of a group of scores, right? So in the last chapter, we looked at an individual score in relationship to a population of all the scores, and we calculated the z-score. However, this is not realistic as far as research goes. We're not looking at one individual person in our research. That never happens. We're looking at groups of people called a sample. And the sample is an estimate of the population, and so we can then turn the sample into a z-score. So instead of looking at the individual, we're looking at the sample mean, and we're computing a z-score based on the sample means. And since we're using a sample to estimate a population, we have to bring up the idea of sampling error. So every time you take a sample from a population, you don't necessarily get the exact population mean. Well, because you can get a various number of people in your sample, and it's going to be a little bit off. Very rarely do you get the exact population mean to be equal to your sample mean. And so the difference between the sample mean and the population mean is known as sampling error. This is completely random. So this is not a problem. This is pretty much known and accepted, that every time you take a sample from the population, the sample mean will not be exactly equal to the population mean. Although we're using the sampling mean as an estimate of the population mean, they're not going to be exactly the same. So any difference between the sampling mean and the population mean is sampling error. Now, this is chance. So I may use the word chance and I may use the word sampling error when it comes to talking about hypothesis testing. They're really the same thing because sampling error is just a chance fluctuation of the sample mean differentiating from the population mean. Now there's a few ways we can minimize sampling error, and probably the easiest one is to take a big sample. So the bigger the sample, the less likelihood of sampling error there's going to be. So you don't want to have a sample of 5 people because you're going to have a lot of sampling error. But if you have a sampling of 500 people, if your sample is 500 people, you're going to have much less sampling error. So that's one way to try to go about minimizing this, but you're always going to have some sampling error. And if you take samples at random from a population, you're going to see that most of the samples are going to be close to the population mean, but some of the samples you take are going to be further away. And this is all based on a normal distribution, and we're going to get into the sampling distribution of means and how it follows a normal distribution shape. So most of the sampling error is going to be small, but occasionally you're going to have larger sampling errors. If you're, I guess, unlucky and you take samples that are kind of not as representative of the population. So as I was mentioning sampling error, which is the difference between the sample mean and the population mean, we could also talk about the sampling distribution of the mean. So basically what the sampling distribution of the mean is, if I took every sample possible of a given size from a population, and I computed the mean for every possible sample, and then I plotted those means, that would give me the sampling distribution of the mean. So I have to take all possible samples of a particular size, depending on what your sample size is, from the population at random, so it could be random samples, and a random sample means that every member of the population has an equal chance of being in the sample. If I were to do that, all possible samples of a given size, and I were to plot the means of those samples, and I would form a distribution, it would be called the sampling distribution of the mean. And basically what that sampling distribution of the mean is, it's a distribution that if you took a sample of that size from the population, that's what you would get, basically. So the majority of the times you're going to get a sample with a mean that's close to the population mean. But on occasion, you can get a sample with a mean that is farther away from the population mean, which is another way of saying it has greater amounts of sampling error. And the good thing about this is that the sampling distribution of the mean will be a normal distribution if your sample size is 30 or more. It's guaranteed to be a normal distribution. The sampling distribution of the mean can also be normal if the population is normally distributed. But that requires you to know what the population looks like, and a lot of times we don't know that. So the easiest thing to do is make sure your sample is 30 or more, because if it's 30 or more, you're guaranteed to have a normal sampling distribution of the mean. And this is going to be a little bit more complex of a topic because we've gone from distributions, normal distributions of individual scores with the z-table, and now we're going to normal distributions of sample means, which seems like a completely new topic, but it really isn't. All you're doing is you're replacing those individual scores with sample means. So the distribution is not made up of individual scores, the distribution is made up of sample means of a given size. And it's treated the exact same way we treated individual scores, and we use the exact same Z formula and the Z table that you did before. So as I mentioned, sampling distributions is when you plot every sample statistic coming from a sample of a given size. And most of the time, almost all the time, we're using the sampling distribution of the mean. So we're plotting the means of those samples, every possible sample from a population of a given size. But you could use the sampling distribution of the variance. So if you were doing sampling distribution of the variance, you would take samples of a given size, let's say samples of 30, every possible sample that you can get from the population of size 30, and you would calculate the variance of each of those samples. So we're talking about hundreds, if not thousands of samples. And then you would plot each of the variances. Then you would have the sampling distribution of the variance, which isn't all that useful aside from certain situations with ANOVA that we can look at, but it's not as useful as the sampling distribution of the mean. So we don't have to just have sampling distribution of the mean. We could have sampling distribution of variance. You could have sampling distribution of a variety of things, of any statistic. But the mean, the sampling distribution of the mean is the most important one because that's used for hypothesis testing predominantly. And when we calculate the sampling distribution of the mean, which once again is every possible sample of a given size, and then you plot all those sample means, the sampling distribution of the mean will have scores piled up near the population mean. And it will be normally distributed if the sample size is 30 or more, or the population is normally distributed, if you know what the population shape is. The larger the sample size, the closer those sample means will be to the population. So the smaller the sampling error will be. So that's the benefit of trying to use a larger sample size, is you get an estimate that is much closer. So a large sample has a mean that's much closer to the mean of the population. There's a lot less variability. If you have a very small sample size, now you're going to have a much greater variability in terms of the means of the sample, and you're going to have much greater sampling error. So one of the goals in research is get a large sample. As much as you can gather and as much as you can afford. There are limits to getting a large sample. A lot of it's money or time or both. Unless your population is very limited. If your population is like college students, there's no excuse not to get a large sample unless you run out of money or you're trying to do it really quickly. And one way to go about this is do it online. You can get thousands of people in your sample. And if you have thousands of people in your sample, you're going to have much smaller amounts of sampling error. You're going to be better able to estimate the population mean based on the sample mean. So you have much smaller amounts of sampling error, and that's going to allow you to test your hypotheses more efficiently. And we'll talk about that in later chapters. So here's an example the book gives you in terms of developing the sampling distribution of means. So in this scenario, this is not obviously a realistic scenario. This is just an example. There's only 4 scores, and those scores are 2, 4, 6, and 8. So the population here in this made-up example is 4. There's only 4 members of the population, and there's 4 scores, 2, 4, 6, and 8. Now, if you look at the shape of this population, there's only one of each of these 4 scores, so the shape of the population is rectangular or uniform. It's not normal because you have an equal number of frequency for these 4 values, so it's rectangular or uniform. So it looks like a rectangle. Now, this could be a problem when it comes to the sampling distribution of the mean, right? So the sampling distribution of the mean is not guaranteed to be normal with a small sample, especially if the population is not normal, and it's not, it's rectangular right here. But let's compute the sampling distribution of the mean based on these 4 scores in the population. So here is the sampling distribution of the mean for the given population, those 4 items, which are 2, 4, 6, and 8, for size 2. So this is the sampling distribution of the mean for a sample size of 2. Now, once again, this is all just for an educational experience. This is not realistic. You would never have 4 members of the population and take a sample size of 2. It's just not realistic. But to sort of help you generate the sampling distribution of the means, it's useful to use a very small problem like this. So if I were to take all possible samples of size 2 from this very limited population, which consists of only scores 2, 4, 6, and 8, I would then plot their means, and this is what their means would look like if plotted. So there are 16 possible samples of size 2 taken from that population of 4 scores. So the first sample would be 2, 2. So you drew it 2 the first time, you replaced it, because this is all done with replacement, and then you drew the 2 the second time. So the first sample would be 2, 2. The next sample would be 2, 4. So you drew the 2 the first time, and you drew the 4 the second time. And then you'd have 2, 6, and then you'd have 2, 8. And you would then replace that, then you would then complete all 16 possible samples. So once you're done with 2, you would start with 4. And it would be 4, 2, and then 4, 4, 4 comma 6, 4 comma 8, and then you would do that for 6 and 8 as well, and you'd have 16 possible samples. If you were then to compute the means of those samples, there's only 2 people in the sample, so you just add the 2 numbers and divide by 2, and you get the mean. You'd have 16 sample means once you've computed the means of those 16 samples. And if you were to plot those 16 sample means, you would have what is appearing here on this slide. As you can see, you have one mean that's 2. Well, obviously, the only mean that's 2 would be for the sample 2 comma 2. So if I took the sample 2 and 2, the mean of that sample would be 2. There's only one instance of that. If I took the sample 2 comma 4, the mean of that sample would be 3. So you see the block over 3. But you also have the same situation when the sample is 4 comma 2. The mean of 4 comma 2 would be 3. So you see there's 2 instances of 3. And you just repeat this for all 16 sample means. You plot the histogram here. You see the 16 boxes on the screen. And everything sort of targets around 5. So this mean of this distribution, everything's clustered around 5, looks to be 5. So this is the sampling distribution of the mean. And the mean of this sampling distribution of the mean looks to be, from this picture, 5. That's the mean of this sampling distribution of the mean. I know it sounds crazy, it's complicated. It's not that complicated, it's just a little bit of an abstract term that you're going to have to process. You're used to looking at individual scores. Now you're looking at means being plotted. That's the only difference. This is the mean of this distribution of means. Now, if you were to compute the mean of the population, so remember, there's 4 members of the population. You had a score of 2, you had a score of 4, you had a score of 6, and you had a score of 8. So let's find the mean of that population. 2 plus 4 is 6, plus 6 is 12, plus 8 is 20, divided by the 4 members, so it's 20 divided by 4 gives you 5. So the mean of the population is 5, and guess what? The mean of the sampling distribution of the means is also 5. So the mean of this distribution is 5, and it's equal to the population mean. And that's always going to be the case. The mean of the sampling distribution of the mean is going to always be equal to the population mean. And you can see it in this example. So everything I said on the previous problem demonstration involved the elements of the central limit theorem. So the central limit theorem allows you to understand what the mean of the sampling distribution of the mean represents. Specifically, the mean of the sampling distribution of the mean will be equal to the population mean. And you saw that with the 5. So 5 was the mean of the sampling distribution, and 5 was the mean of the population, right? So once again, I'm going to repeat it because it's a little bit, long-winded. The mean of the sampling distribution of the mean is always going to be equal to the population mean. We also know that the shape of the sampling distribution of the mean will be normal under 2 conditions, which I previously mentioned. The first condition is if the population distribution is normal, then the sampling distribution of the mean is guaranteed to be normal. The second situation is that if your sample size is 30 or more, the sampling distribution of the mean is guaranteed to be normal. So those are the 2 rules that the central limit theorem sort of states. And the third aspect of the central limit theorem is that the standard deviation of that sampling distribution of the mean is known as the standard error of the mean. So the standard deviation of the sampling distribution of the mean is known as the standard error of the mean. And you compute that standard error of the mean by taking the standard deviation of the population, which is sigma, and dividing it by the square root of the sample size. So the standard error of the mean is computed by taking the standard deviation of the population, which is sigma, lowercase sigma, and divide that by the square root of the sample size. And those are the three components of the central limit theorem. One, once again, I repeat it again, central limit theorem, proposition one, the mean of the sampling distribution of the means will be equal to the population mean. Proposition two, the shape of the sampling distribution of the mean will be normal for samples greater than 30, greater than or equal to 30, or if the population is normally distributed. And then the third proposition is that the standard error of the mean is equal to the population standard deviation divided by the square root of the sample size. And those are things you kind of want to just memorize because they're rules, basically, that are used in statistics. And the central limit theorem rules are stated here again, that as the sample size approaches infinity, the sampling distribution of the mean is normally distributed, but we use the rule of 30 or more. So when your sample is 30 or more, it's fine to say that the sampling distribution of the mean is normal. And then the population mean is equal to the mean of the sampling distribution of the means. And then the standard error is equal to sigma divided by square root of n. Shape of the sampling distribution of the mean is you need to have 30 or more. That's why you need a bigger sample. Or you have to know that the population is normally distributed. Warning, you don't know this most of the time. If you're doing research, you don't know what the population is. You don't know the population mean. You don't know the population standard deviation most of the time. And if you don't know that, then you can't use Z that we're using in this chapter. You would need to use an alternative to Z. But if you don't know the shape of the population, then you really need you need those 30 scores or more. That's kind of the emphasis here. Get a sample of at least size 30. If you don't have size 30 and you can't guarantee normality of the sampling distribution of means, then you're kind of in trouble. And you'd want to use non-parametric tests, which are beyond the scope of this class. You'd have to use like these, they're kind of like gimmicky tests. They're not really good to use. And they're not really well known, I guess, for like introductory students. They're more, they're more for researchers that have a problem with their sample size. And they're not really a good idea to use them, these non-parametric tests. One is called the sign test, or there's something called the Wilcoxon rank sum test. That's a little better than the sign test. The sign test is also known as a binomial test. Some of you may be familiar with this from Math 150, the introstat stuff. But this is not the way to go. Like as a researcher, you don't want to go that route because you're not gonna really support your hypothesis if you're using these non-parametric tests. It becomes very difficult to get good results. So as a result, you want sample size of 30 to guarantee the normality of the sampling distribution. Now, according to the central limit theorem, the mean of the sampling distribution of means is denoted here as mu sub m, and is equal to the population mean. So this mean of the sampling distribution of means is unbiased because it's exactly equal to the population mean. So this is an unbiased statistic. And that's important. You saw bias versus unbiased statistics when it came to the standard deviation and the variance, right? So if you're doing the sample variance, you're dividing by n minus 1. If you're calculating the population variance, you're dividing by n. And the reason I use n minus 1 in the case of the sample variance is because that's an unbiased statistic. That means it gets you the actual value, the real value that you want. And the same thing is happening here with the mean of the sampling distribution of means. It's an unbiased statistic, so it's equal to exactly the population mean. And that's why it's so important. So we don't need to know the population mean if we have our sample. Because once I calculate the sampling distribution of the mean, we know the population mean. And the standard error of the mean is the standard deviation of that sampling distribution of the mean. So once you calculate that sampling distribution of the mean, which is all possible means of a given size, and you plot it all out, if you were to calculate the standard deviation of that sampling distribution of the mean, it would be known as the standard error of the mean, which is written as sigma sub m. And sometimes it's written as SE. You might see SE as standard error. You generally don't see SEM because SEM means structural equation model. And so in a journal, you won't see SEM to refer to the standard error. You'll just see SE. So SE or standard error are the general way to refer to this. Now, the one thing about the standard error of the mean is it depends on the sample size. So if you have a large sample, the standard error of the mean is going to be smaller. If you have a small sample, the standard error of the mean is going to be larger. For research purposes, we want a small standard error of the mean. Because the smaller the standard error of the mean, the better ability to support our research hypothesis. Because we're going to get a larger value for, in this chapter we're calculating Z. In another chapter we'll calculate T. So the smaller your standard error of the mean, the larger your inferential statistic that you're computing, and the easier it is to reject the null hypothesis. So the easier it is to support your hypothesis. And that's why we want the sample size to be big, because once the sample size is big, the standard error of the mean is small, and it's easier for us to find, to support our research, basically, to support our hypothesis. And this is known as the law of large numbers. So the larger our sample size, the more probable that our sample mean will be close to the population mean. So once again, bigger samples are better. If the population variance is smaller, then our standard error of the mean is going to be smaller. The problem is that a lot of times we don't know the population variance. So in the last slide, I talked about how the sample size is important for making the standard error of the mean small. So if I have a large sample, my standard error of the mean is going to be smaller. That's the easiest way to reduce the standard error of the mean, is get a larger sample. However, if the population variance is small, then the standard error of the mean is going to be small too. The problem is you don't know, much of the time you don't know what the population variance is because you don't have all the population data. If our population is BMCC students, I need to know all the BMCC students. I'd have to have access to all of them. That's not realistic. So if I don't have access to everybody in my population, I won't be able to calculate the population variance. However, if you're studying something that's been studied before, you may have some population variance estimates. So like IQ, it's been studied over and over again. And since it's been studied so much, we know that the variance is around 15. The standard deviation is 15, I should say. The variance would be double that, so it'd be 225. I mean, squared 15. I'm sorry. So there are certain situations where we know the population variance, but in the vast majority of cases we don't. And it's just easier getting a bigger sample rather than worrying about figuring out the population variance and how that's going to affect your research. Here's a graph depicting the size of the sample and the standard error. So as you see, as our sample gets bigger and bigger, the standard error gets smaller and smaller as we go to the right on this graph. Now the biggest drop is around 30. It kind of plateaus. You see 36, it's kind of plateauing there. It's kind of asymptotic at this point. But you see the huge decrease in standard error from a sample size of 1, which is an individual score, compared to a sample size of 36, right? It goes down pretty rapidly. And that's why you want those samples of 30 or more, because you're going to get much smaller standard error than means. Here's a situation where we're looking at the original population of IQ scores. Once again, the mean of the IQ is 100 and the standard deviation is 15. And now we took a sample of 25 IQ scores from that population. So I took a random sample of 25 scores. I calculated the mean, and the mean of those 25 scores is 101.2. That's pretty close to 100, right? So that's a pretty good, estimate of the mean. There's very little sampling error there. There's only a difference of 1.2 from that sample. But you see that the standard deviation of the sample is less than the standard deviation of the population. It's 11.5. Standard deviation of the population is 15. Now, if I were to calculate the sampling distribution of means, so if I were to take every possible sample of size 25 and I were to compute the mean of every possible sample of size 25, and I plotted those means, you would get what you see in part C here. And as you can see, that's a normal distribution. Well, it's guaranteed to be normal because the original population is normal. So therefore, that sampling distribution of the mean is guaranteed to be normal. You see the mean of that sampling distribution is 100, and that's exactly equal to the population mean of 100. But you see the standard error is much smaller. The standard error is 3. So the standard error would be 15 divided by the square root of 25. So it'd be 15 divided by the square root of 25 is 5. 15 divided by 5 gives you 3. And so it's much easier to reject the null hypothesis, or another way of saying it's much easier to support your research hypothesis when the standard error is small, like 3, than compared to when the standard error is large, like 15. So when you computed z-scores before, you computed it on populations, like you see in figure A. That's the population. And you did z equals x minus the mean over sigma. While sigma here is 15, so it's going to make z pretty small compared to situation C, picture C here, where sigma is 3. So the z is going to be much larger here because you're taking a larger sample. And so that's the advantage of taking a larger sample, is that your standard error is going to be smaller. It's going to be easier to then get a bigger z value. And the bigger z value is going to make it easier to support your research hypothesis. And that's why we should always test on samples rather than individuals. One, because individuals vary tremendously. You can't make sense of research based on one individual. It becomes a case study, and it becomes kind of useless to draw conclusions in terms of research. But if you have a sample, even a sample of 25 makes it so much easier to thoroughly investigate your research hypothesis and come up with an answer. And easier to support your research hypothesis in general as well. Now, that doesn't mean that if you have a large sample, you guarantee to support every hypothesis you come up with. That's not the case. although you're going to be a lot more likely to support your hypothesis with a large sample. And it can be abused. Like if you take a sample of 5,000, it's going to be very easy to support whatever hypothesis you have because the sample is so big, which makes it kind of tricky, as far as like publishing that research. With a sample of 5,000, someone's going to say, wait a minute, uh, pretty much any idea you have, if you run 5,000 people, you're going to support your idea. And so they're going to want to look for other measures other than just the probability of supporting your idea that we're talking about in this chapter and in chapter 6, where you looked at the Z table. They're going to want more than that with large samples. So you want a large sample, but you don't want it to be like obnoxiously large to the point where statisticians or reviewers or people like myself are going to say, wait a minute here, this is kind of like inflated. Your values are inflated, and therefore I don't really believe in your research. And that's one of the problems with the system we're using, which is called null hypothesis significance testing. That's an issue, is that it's very prone to inflating the sample size, and that pushes your result towards statistical significance, which means that you're going to support your ideas. And so be careful of the overly inflated samples. So you don't want like 5 people, but you also don't want 5,000. Take something in the middle, 100, 200, depending on your discipline. In psychology, 100, 200 if you have the ability to do it, that's fine. No one expects more than that, but you also don't want really small samples either, because it's going to put you in trouble. You're not going to be able to support your ideas that way. So learning check 1. The population has a mean of 60 with a standard deviation of 5. We're calculating the distribution of sample means of sample sizes of 4. What would be the expected value? So what would be the mean of that sampling distribution of the mean? Well, we know from central limit theory that the mean of the sampling distribution of the mean is equal to the population mean. So that mean of that sampling distribution of whatever size it is has to be 60, because that's what the population means. And that's what the answer is, of course. The mean of the sampling distribution of the mean must be equal to the population mean. True or false? These are questions I would never put on an exam, like true or false. I don't believe in true or false questions, but it's important as far as like understanding sort of the totality of the concepts. The shape of the distribution of sample means is always normal. Well, we talked a lot about that before. There are certain conditions that have to take place before we declare it normal. In statement 2, as sample sizes increase, the value of the standard error decreases. Well, we also looked at that calculation as well, and I keep emphasizing large samples because that leads to the ability to support your own research hypothesis. So that's a good thing. So of course, the first statement is false. The shape of the sampling distribution is only normal if the population is normal or the sample size is greater than or equal to 30. That's central limit theory. And the second statement, of course, if you increase sample size, you decrease the standard error. So as n gets larger, the standard error goes smaller, and that's a good thing as far as testing our hypothesis. We're able to then support our hypotheses when the standard error is smaller. Now, converting this all into z-scores. So using the distribution of sample means allows us, given that that distribution is normally distributed, right? That allows us to convert everything to z-scores. So converting a mean to a z-score is the same process as converting an individual score. So just like we did with x, we're just going to replace x, we're going to replace it with the mean of the sample, which is m. So I'm replacing the raw score x with the mean, which is m. I'm also replacing sigma, the standard deviation of the population, with the standard error of the mean. So sigma changes to sigma divided by square root of n, which is the standard error. And so the rest of it's the same. So all I'm doing with the z-score formula is I'm changing x to m, the mean of the sample, and I'm changing sigma to the standard error, which is sigma divided by the square root of n. And then I compute z, and I use the same table that I used before. The sign of the z determines whether it's above or below the mean, and the number tells you the distance in terms of standard error units, above or below the mean. And here's the formula. Z equals the mean of the sample minus the mean of the population divided by the standard error, which is sigma divided by square root of n. And then you get a z value, and that tells you the number of standard errors above or below the mean that that sample mean is at, right? So it tells you basically the location of the sample mean in terms of standard error units. So this is a distribution of sample means for a sample size of 16. So if I were to take all possible samples of size 16 from a population with a mean of 500 and a standard deviation of 100, and I were to plot them, and this is a normal, the population is normally distributed, this is what the sampling error of the mean would look like. It would look like this curve, this normal curve. We know that the mean of the sampling distribution of the mean is going to be equal to mu, the population mean, which is 500. And we know that the standard error of the mean is equal to sigma divided by the square root of n. Well, sigma here is 100. 100 divided by the square root of 16 is 100 divided by 4, which is 25. So the standard error of the mean in this problem is 25. You see that denoted on the screen. The further you are away, so the closer you are to the tail of the distribution in terms of research, the better you are, right? So as a researcher, I don't want to be towards the middle of this distribution. I want to be in the tail. And the reason I want to be in the tail is that this sampling distribution of the mean generally represents what would happen if there was no effect. So there was no impact of the independent variable, there was no effect, or there was no treatment effect, right? If I'm doing intervention study. So this sampling distribution of the mean only represents chance. Chance means just random variation or sampling error. It means the situation where there was no effect of the independent variable. So whatever you did not work. That's what this sampling distribution of the mean represents. It represents the situation where your study did not work. Your intervention did not have an effect. So if I were to do some kind of intervention and I were to calculate the mean of that sample that got the intervention, I would want that mean to be further in the tail because I don't want it anywhere near the mean of the no treatment effect, right? I don't want it even associated with this distribution because this distribution represents no difference or no effect. More technically, it represents something called the null hypothesis. So I want my sample mean to be in the tail as a researcher. The further it is in the tail, the more likely I can say that this sample does not belong with this distribution of no effect. In order for it to be in the tail, the z-score has to be large. You see the z-score on the horizontal axis. I want that z-score as large as possible. I definitely want it greater than 2 because that's where the tail starts. The bigger it is, the better as far as research goes because that allows me to support my research hypothesis. That allows me to say that whatever I'm doing, whatever treatment I'm using, or whatever the independent variable is, it's working if it's in the tail. If the sample mean's in the tail, it's working. If the sample mean's closer to the 500 in the middle of this, it's not working. That's not what I want. And so in the same example, actually a different sample size here. So the same 500 and 100, 500 the mean, 100 the standard deviation. We've increased the sample size to 25, and so then the standard error becomes 100 over the square root of 25, which is 100 over 5, which is 20. So the standard error is 20. But in this situation, we want to find what values for the mean, for the sample mean, will include 80% of all possible sample mean values. So I have to find the z-score that corresponds to 80% of the distribution, 80% of the middle of the distribution, which means 40% on the right and 40% on the left. So I can look in the z-table for mean to z, and I want that mean to z column to be 40%. And when I look up in the table mean to z for 40%, I find 1.28 on the positive side and negative 1.28 on the negative side. So those two z-scores represent 80% of the middle of the distribution, which leaves 10% in each of the tails. As a researcher, I want my score in the tails, and as far in the tails as possible. So I don't want it even close to the 1.28. I want it much further in the tail. But if I were just to calculate what are the two scores that cut off the middle 80%, I could then just find those z-scores, multiply it by the standard error, which is 20, and then add it to the mean on the right and subtract it to the mean on the left. And those two values for the sample means, 474.4 and 525.6, those are the two cutoffs that delineate or separate the middle 80% of the distribution. So that cuts off the top 10% of the tail on the right and the bottom 10% of the tail on the left. And as a researcher, I want to be in those tails. Of course, I've mentioned sampling error a million times already. The difference between the sample mean and the population mean is called sampling error. If my standard error is smaller, my sampling error is smaller. If my standard error is larger, my sampling error is larger. The goal, of course, is to have standard error smaller and therefore the sampling error smaller. And one way to bring about this goal is to have a large sample. So increase sample size, you reduce the standard error, and you obviously reduce the sampling error by doing that. So here is just a diagram of many samples of a given size taken from a population. So there's tons and tons of samples. Each box represents a sample here. So this is the sampling distribution of the mean. You see it's normal, you see it's symmetrical about the population mean, right? These are all sample means being plotted. Now let's look what happens when we change the sample size to this sampling distribution of the mean. So if my sample size is 1, which means I don't really have a sample, I have individual scores, the sampling distribution of the mean is going to be equal to the population standard deviation. So the standard error of the mean is equal to the population standard deviation when our sample size is 1. Because how do we calculate standard error of the mean? The standard error of the mean is sigma, which is 20, over the square root of n. Well, 20 divided by the square root of 1 is equal to 20 divided by 1, which is equal to 20. So I'm getting no benefit from a sample of 1 because my standard deviation is large, and with a sample of 1, that's going to be my standard error. And you see how the curve in figure A, it's all spread out. That's not good, because now it's going to be hard for me to get into the tail of the distribution. It's going to be much harder to get into that tail because the scores are really spread out. This sampling distribution of the mean is not ideal, and the reason it's not ideal is because the sample is 1. You would never, under any circumstance, the whole purpose of sampling is to have something larger than one so that you reduce, the error that you get with individual scores. So you don't have that in figure A. You have a mess of a situation there. It's going to be really hard to support your hypothesis in figure A. In figure B, we have samples now of 4. Now that's not ideal, but it's a lot better than 1. And look what happens to the standard error. The standard error goes from 20 all the way down to 10 with only a sample of 4. Because what happens is it's sigma over square root of n, so it's 20 divided by the square root of 4, which is 20 divided by 2, which is 10. You've seen now that it's a lot better situation than in figure A. Now you can actually reject the null hypothesis. You can actually support your research with a score in the tail. It's much easier to get in the tail here because the standard error is smaller, so it's easier to be in the tail in figure B. And in figure C is the perfect situation. Now my sample size is 100, and look what happens to the standard error. It goes from 20 to 10, now it's all the way down to 2. So it's 20 divided by the square root of 100, which is 20 over 10, which is 2. Look how narrow the distribution is in figure C. So here, it's very easy to get into the tail. And since it's so easy to get into the tail, it's much easier to then support your research hypothesis. Remember, the goal for the sampling distribution is to get out of the middle and be in the tail, either tail, the positive or the negative tail, depending on your hypothesis. You want to be away from the middle and close to the tail. That's the goal of research. And that's much easier in figure C than it is in figure B, and way easier than in figure A. As I mentioned previously, journals either use SC or SEM for the standard error. I would use SE personally, because SEM is confusing because it stands for structural equation model. And there is a statistical technique called SEM. It's an advanced version of regression slash factor analysis, principal components analysis. It's way too advanced for this class, but you'll see it often in journals. And so I would not use SEM. I would just use SE as standard error. I don't understand why the text reports SEM. Don't use SEM. Use SE. You'd also report the sample size and the means for the sample, and then you would add graphs as well in your write-up if you were to write this up as a study. You always want to use graphs because graphs really tell a story, right? Here's a simple bar graph between two groups, Group B and Group A. You want to see if there's a difference between Group B and Group A. We've added the standard error of the mean here. So what they've done in this picture is they've added this error bar. So you see that bar that's extended from each graph, from each bar here. You see that line that goes down. And you see the top whisker and the bottom whisker. Those are error bars. So this represents one standard error of the mean, plus one standard deviation of standard error of the mean, and then minus one standard error of the mean. So the actual mean of Group B is where the, if you look at Group B, this, I guess this is aquamarine. I don't even know what color this is. Some kind of off blue, some different blue version here. I don't think it's aquamarine, but it's kind of a heavier, aqua blue, not aquamarine. You see the mean is the top of the blue bar here. That's where the mean of Group B is. Those whiskers that are extending it are plus one standard error, positive, up, and minus one standard error, down. The goal of these these error bars, these whiskers on the bars here, is to see if these groups differ by standard errors. That means that if there's no overlap in these error bars, that means the groups differ significantly from each other. That is not due to chance. These error bars represent chance. They represent sampling error. So basically, the true population mean for Group B could be anywhere in these whiskers, the high end and the low end. So there's an error here because we're using a sample to estimate a population. So there's some kind of error, right? And the same thing with group A. The true population mean for group A is somewhere between the lower whisker and the upper whisker. Now, this is only one standard error. Ideally, you would use two standard errors to then really look at differences. If the bars don't overlap, then we can say that these two groups are truly different from each other, that the difference is not due to sampling error. If the bars do overlap, then we can say that there's really no difference between these groups. The differences are due to sampling error. So the goal of research is to have these error bars not overlap. And in this situation, they don't overlap, but remember, this is only one standard error above and below. You can use more than one. And this is how you develop something called a confidence interval. And we like to use a 95% confidence interval when we test hypotheses. So the text doesn't really go into confidence intervals at this point, so I'm not going to go into it. But basically, in this situation, you are confident that the true population mean is within these whiskers, these error bars. And if you increase the number of standard errors, you increase the confidence that the true population mean is in that interval. So here you're going to have like probably a 60-something% confidence that the true population mean is within these error bars. If I increase it to two standard errors, it's going to be up to 95%. So it's 68% here, and it's going to go to 95% with two standard errors. So the moral of the story is try to add, two standard errors above or below instead of one, like this picture shows. This is a different kind of graph, but it's the same concept of error bars. But here we're using a line graph because we're looking at changes over time. So whenever you're graphing changes over time, you can look at a line graph like this instead of a bar graph. And you see that group B is going down over time. These are mistakes in whatever situation this is. You see there's a downward trend from group B. There's also a downward trend from group A, but it's not as clear. Group B is a more significant downward trend. But these error bars don't overlap. So at every single point of time, every single trial here, there's a significant difference between group A and group B. Now, what's happening is the error bars are increasing at certain points. So look at trial 2. The error bars are larger. So that means there's a lot more variability there for whatever reason. Something in trial 2 led to a lot more variability compared to trial 1, where there's a lot smaller variability. Remember, this is like the graph I showed you where we had a large standard error versus a small standard error. In trial 1, both group A and group B have small standard errors. See how the bars are clustered? There's small amount of bars here. They're clustered around the points, the means. So those are small standard errors. In trial 2, the standard errors got much bigger. So I'm not sure what's going on there. There's something about trial 2 that led to a lot more variability. Whatever that is, that's interesting to know. But they don't overlap, so that's good. They're still different because there's no overlap here between group A and group B. It's just that the standard errors got much bigger. And then you see in trial 3, there's a little bit of a mix. Standard error for group A is smaller. Standard error for group B is a little bit larger for whatever reason. And the same thing in trial 4. Group B, the standard error is small, and group A, the standard error is larger. So you can have this. I mean, there's a bunch of dynamics going on here. That group A is different than group B, and there's a lot more variability across trials for whatever reason. They change over time, right? Something happened in trial 2 and trial 4 that led to a change in variability. Whatever it is, that as a researcher, you have to figure that out. This is just a purely statistical look at it, but this is a question that needs to be answered by the researcher. Why is there a change in variability over time? And as I've been mentioning over and over again, we use inferential statistics to take a sample and draw conclusions about the population. Remember that the sample is not completely accurate of the reflection of the population because there's sampling error. And so we have to decide, you know, is this sample significantly different than the population or is it similar to the population? And we do that by computing z-scores and then looking up the table and finding probabilities. So for example, if we're doing an experiment with adult rats, I'd love to do experiments on rats, right? And if you've ever done experiments on rats, you realize that it's troublesome, right? They're not the most cooperative participants in research. Rats, they don't want to be there. So they weighed adult rats, and the population of adult rats had a mean weight of 400, and the standard deviation is 20. So that's basically the average rat, adult rat, has a mean of 400 in terms of weight and a standard deviation of 20. I'm assuming this is grams, right? Sample of 25 rats are taken. So they've taken a sample of 25 rats from this population with a mean of 400, standard deviation of 20. They give the sample a treatment. So they inject them with something to alter their metabolism or alter their weight or their food intake, right? So this could be easily done if you're testing a medication for weight loss or obesity. You don't want to test it on humans first. You want to test it on rats to make sure there's nothing, serious side effects or something bad happens to them. So you take those 25 rats, you inject them with this drug, right? That's the treatment. And now you look at the mean of those treated rats. So after they got their injections of whatever drug you're giving them, you want to see how much do they weigh. If you're giving them a drug to make them lose weight, you want to make sure that their weight goes down. So their weight should be less than 400 because 400 is the untreated rats. That's the population that's untreated. If your drug works and it's going to cause weight loss, then that sample of 25 rats should have, a mean weight, an average weight to mean weight of less than 400. That's the goal. So you should have a negative z-score here. Right? You want that z-score to be negative. You want it to be really far negative to the left. You want it to be in the tail of that distribution. And that would allow you to say that the sample has lower weight than the population, if that's your goal, to reduce weight. So one way to do it is to look at the what's called the 95% confidence interval. So you want to look at the two scores that basically divide the distribution up so that there's only 5% in the tails. And that's what you have here. So you have only 5% in the two tails total. So these two scores, z-score of 1.96 and the z-score of negative 1.96, delineate the middle 95% of all scores. Right? Because remember, we were talking about last week, one standard deviation above and below the mean represents 68% of scores, and two standard deviations represent 95% of scores. Well, this is two standard deviations, so it's 1.96 is close to 2, and negative 1.96 is very close to negative 2. So these two scores, z-scores, represent the cutoff for 95% of all scores in the middle, in the population. The population where the mean is 400, the standard error here is 4. Right. So those two weights that block off 95% of the distribution are 407.84 and 392.16. So there's two tails here. There's a tail to the right and a tail to the left. If we're looking for the drug to cause weight loss, we're not interested in the tail to the right because the tail to the right represents weight gain. So I don't want my sample to be in the right tail here because that means the rats gained weight. I don't want that. I want the rest to lose weight. Because if I'm trying to find a weight loss drug and I'm giving it to these rats, I want them to lose weight. I don't want them to gain weight because if they gain weight, well, I'm in trouble. Basically scrap it, start over. because that's what you're looking for. I mean, when pharmaceutical companies look to develop drugs that alter weight, they're looking for drugs to make people lose weight. They're almost never developing a drug to make people gain weight, because the vast majority of people need to lose weight versus gain weight. So I want my results as a researcher to be in the left tail. So I want my z-score for my sample to be less than negative 1.96. So I want it in the far left tail here. That's the goal. I want that sample to have a mean that is below 392.16, because that's showing that there's weight loss. So 8 grams in a rat is pretty good, is pretty big, right? I mean, 8 grams. That's 1/50th of their total body weight. If an individual lost 1/50th of their total body weight, that could be a few pounds. You're not going to get a treatment that's going to make someone lose like 10% of their body weight. That's really difficult. We're talking about a pharmacological intervention that is going to be small but consistent. There's a lot of behavioral things people have to do to lose weight too, like exercise and eat less. So the drug is going to help, but it's going to only help a little bit. You have to use other things to help as well. So if I just give the injection to the rat, I want their weight in the sample that I gave the injection to, the sample mean of 25 rats, to be less than 392.16. Because if that's the case, then I'm going to say that the treatment works, because it's always in the left-hand tail. So it's not likely to belong to this population of untreated rats. So this population of untreated rats has a mean of 400. If my sample is way in the left tail, then it doesn't belong to this population of untreated rats. It belongs to an alternative population of rats that have lower body weights than 400, which is my goal, right? I don't want it to belong to the 400 group, because that means it didn't work. I want to belong to a population that you don't see it here, but it's here. It's to the left of this curve, where the mean of that sample is less than 400. That's how I say that the treatment works, because then it's not due to sampling error. Because if it's always in this tail, in this left tail, it's not due to sampling error. It's due to the actual treatment. If it's closer to the middle here, then it's probably the difference is due to sampling error and not due to the treatment. So that's the main goal behind hypothesis testing. We're going to be doing this ad infinitum for the next, I don't know how many chapters. We're going to be doing like all the different inferential tests, but the concept is the same. You want your results, you want your sample to be in the tail rather than be in the middle of this population here. This is the sampling distribution of means, and the sampling distribution of means represents no effect, no treatment effect, no effect of the independent variable. It represents what's called the null hypothesis. Basically, nothing happened. So the tail is where we want to be. In this case, we want to be the negative tail because we're looking for weight loss. We don't want to be in the positive tail because that's weight gain. We want to be in the negative tail. Let's do a couple more problems before we wrap this up. A random sample of 16 scores is obtained from a population with a mean of 50 and a standard deviation of 16. If the sample mean is 58, the z-score would be what? Well, we can plug this in and convert the z-score. So z is equal to the mean minus mu, so sample mean, which is m, minus mu, divided by sigma over the square root of n. So z equals m minus mu over sigma divided by square root of n. So when I plug that in, I get 58 minus 50 divided by 16 over the square root of 16, which is 4. So it becomes 58 minus 50, which is 8, over 16 divided by 4, which is 4. 8 over 4 gives me 2. So the answer is B, 2. And that's what we're getting here. We just plug into the z-score formula, And all you're doing is replacing x with m, and you're replacing sigma with the standard error, which is sigma divided by the square root of n. That's all you're doing. It's the same formula, just those two scores are being replaced. True, false. A sample mean with z of 3 is a typical representative sample. Well, you have to think, where is z? Is z in the tail or is z towards the middle? Last time I checked, z is in the tail. It's pretty far in the tail. So is that representative or not? And the second question, the mean of the sample is always equal to the population mean. Now this is one sample. So is the mean of one sample always equal to the population mean? You should know the answer to that. Of course, the first statement is false because the z-score of 3 is in the tail. So it's very unlikely. So it's not typical of the rest of the distribution. And one sample does not let you know the population mean. Remember that the mean of the sampling distribution of the means is equal to the population mean. That's every possible sample of a given size. If you just have one sample, there's no way you can tell what the population mean is. Now, if your sample is large, the mean of your large sample should be closer to the population mean than the mean of a small sample. That's the law of large numbers. But it doesn't guarantee that you know what it is. You just know that it's around that particular value. If, however, you have the entire sampling distribution of the mean, then you know the mean of that sampling distribution of the means is equal to the population mean, and that's part of the central limit there. So there's a lot going on in this chapter. It's very complex. It's also difficult to learn online. I mean, it's difficult to learn in class too. I mean, it's a very complex set of concepts here. So you need to read through the text very carefully. Hopefully I gave you a different spin on it, although it is kind of jargony and it is very highly conceptual. So it's something that you're gonna have to go through multiple times, do the problems for the homework, read the text, and then ask me questions. I mean, that's the best way to do this. And also realize that if it's your first time taking a statistics class, that you're not going to get everything the first time through. You want to get the basics, but if there's something, if not everything makes 100% sense, if it's not just like, wow, this makes perfect sense to me, it's not unusual. You need to take several classes to really start understanding these things, and then they become much more, I guess, solid. Right now, it's like a lot of theoretical stuff. So, really understand, focus on the concepts of sampling error, sampling distribution of the mean, understand that sampling error represents chance, and we don't like chance as researchers. We want more than chance, right? And that you want your scores to be in the tails of the distribution when you calculate Z as a researcher. Because that means that your results are not due to chance, that they're probably due to the effect of the independent variable or the treatment. So those are sort of the take-home points, and then you kind of have to memorize the central limit theorem. That's kind of something you just need to know. There's like rules that you need to know, but don't get alarmed if it's your first pass through and you're just like confused, because these are more abstract concepts, and you really need to read the text, and you need to do the homeworks, and you have to really spend time on it, and then follow up with me with questions and stuff, and I can try to explain things in more detail. There's nothing to really sketch out. It's all conceptual. So it's more conceptual than it is problem solving at this point. So hopefully the lecture helped you a little bit and gives you more of a sort of conversational understanding of the concepts. But definitely read the text. The text is written pretty well for the most part. So do that, do the homeworks, contact me if you have a problem. Bye for now. See you next week with more inferential tests.